Consider this system, all of you. There are two blocks connected by a light inextensible string. Okay, that's the most important term here. Let's say the one on the surface is sliding to the right with a speed v1, and the one hanging is moving down with a speed v2. Do you think these two speeds should be depending on each other, or they can move with completely independent speeds? The blocks are connected by a string. So is there any restriction on these velocities, or do you think they can have their own velocities independent of each other? Is there a constraint here or not? Definitely there will be. If you hold that gray color block and don't allow it to move down, then that box also won't slide to the right side. Okay, so how fast the block slides depends on how fast the gray color block is falling down. Okay, so the speeds are related to each other. You have to derive the relation between them. At the moment, let's say the angle between them is theta. See, at a later instant or a previous instant, the angle will be different. Okay, for example, when this box was here, the string would have been making a different angle with the horizontal. Okay, slightly lesser angle. As the block moves to the right, that angle theta goes on increasing. So theta is a variable. At the given instant, take it as theta itself. Before that, it would have been less than theta. After this, it will be more than theta. At this moment, it is theta. Derive the relation between V1 and V2. Try this, all of you. I'll give you 2 minutes. At least tell me an idea. Okay. Any idea, anyone? What, I mean, how can we relate these two velocities? Okay. Recollect and tell me, what are some of the ideas we used to derive constraint relation between two objects? We did that long back. What ideas do we use to derive constraint relation between connected objects?
So total work done.
Okay, good. That is one of the ideas we did use. Total work done by tension on the entire system is 0. Okay, work done by internal forces is 0. Okay, we can make use of that. There are other ways also. Okay, like the total length of the string should remain constant. No, on one side the length of the string will decrease, the other side it will increase. How much it is decreasing on one side should be equal to how much it is increasing on the other side. That idea also can be used. So observe carefully here. We need a relation between their velocities. Okay, we know velocity is rate of change of displacement with respect to time. We will make use of that. The box is moving to the right side and the stone is moving down. Okay. We are going to use the fact that work done by tension on the box plus work done by tension on the stone is 0. There are no other moving parts in this system. Okay. And these are rigid bodies, so work done should be 0. Now work done by any force depends on force displacement and the angle between them. Now I indirectly gave you a hint. The box's displacement is to the right side, okay. But the angle between the string and the box displacement keeps varying. at an instant before, that angle would have been smaller. At an instant later, that angle will be much bigger. Okay, so the angle keeps changing. So it's like the angle between force and displacement keeps changing. Then what to do to derive work? Take a small displacement. So consider a very small displacement of the block like this. Okay, follow the steps carefully, all of you. This is very important. Let's call the displacement as dx. Direction is to the right, magnitude is dx. And consider a small displacement of the block as well. Very small displacement. Call it dy. Direction is downward, magnitude is dy. Okay. Now it's a light inextensible string. A light string will have the same tension everywhere. Okay, massless string. So on the stone, tension acts in this direction. On the box, tension, the same amount of tension acts in this direction. Now let them undergo these small displacements. One of you tell me, how much is the work done by tension on the box? In terms of t, dx and theta, how much is the work done by tension on the box?
dx cos theta.
T dx cos theta. Okay. It's actually T force dot displacement, force dot small displacement. Okay. Okay. I should not say work done also. I should say small amount of work done. See, we know the formula for small work, dw is equal to f dot ds. You don't have to integrate or bother about anything. In a small displacement, you can assume the force is constant, angle is constant. So you can write the small amount of work done by tension on the box is T dx cos theta. One of you tell me how much is the work done by tension, small work done by tension on the stone.
Minus t dy.
Correct. Force is T, displacement is dy, angle is 180, cos 180 is minus 1. So minus T dy. Add these two. T dx cos theta minus T dy should be 0. That's all, cancel T. You get dx cos theta is equal to dy, send dy that side. Dy is equal to dx cos theta. Okay. This is the relation between their small displacements. Simply divide by time on both sides, small time. Nothing wrong in that. You can divide by a positive number on both sides of the equation. It won't change the equation. dy by dt is nothing but speed of the stone. Dx by dt is nothing but speed of the box. That's all. That's the relation between their velocities at the given instant. So, using the fact that work done by tension in a small displacement is 0 on the entire system, we get a relation between their displacements first. Divide displacement by time, like displacement relation, you divide by time, you get a velocity relation. Simple. This is one way to answer this question. There are two other ways that I will tell you. Just a moment. You can ask if you have any doubts. Yesterday, while solving that velocity of rod based question, just a moment, this thing got stuck. This one, we used two methods. One is the fact that their velocities, the velocities of those points along the length of the rod should be common, should be equal. So components we equated. Another one is this trigonometry based, Pythagoras theorem based method. X square plus y square is equal to L square. We differentiated that. We can use that idea in this problem. What we want is the relation between their speeds. Okay, forget tension. Here also there is a right angle triangle forming. Let's call this distance as x. Now this horizontal line is drawn based on the ground. Okay, not based on this block. The block could be slightly higher, slightly lower also. I'll take it slightly lower so that you don't get confused. This is what the situation is like. Okay, and let's call this distance as y. Only from here to here I'll take it as y. Not the total length of the string on the right side. Only this part of the length I'll take it as y. And let's call this as z. Now you know one block goes down, one block goes to the right. Okay, this will move to the right side. The other one goes down. Imagine these blocks moving and tell me which terms out of x, y, and z change. Which are the variable terms out of x, y, and z?
X,
X is definitely a variable. Is that the only one? Just
Z.
imagine. Tell me.
Sir, Z.
Z is also a variable. Okay, if you imagine the box at an earlier instant, this would have been the value of z much longer. Okay, and this would have been x much longer. Y remains the same. Both z and x are variables as the box moves. Okay, now here's a right angle triangle. So you can write x square plus y square is equal to z square. Differentiate this equation. X square derivative, we are differentiating with respect to time, so we use the chain rule. 2x dx by dt plus y square. Y is constant, so derivative of y square will be constant. Derivative of constant is 0, is equal to z square derivative will be 2z dz by dt. Okay, now dx by dt, rate of change of this distance, is nothing but the speed of the box, and z is the length of the string on the left side of the pulley. By whatever amount z decreases, by the same amount this length will increase. This is not y, that length is not y. Let's call it L itself. If z decreases by any amount, L will increase by the same amount. So the rate of decrease of z is equal to the rate of increase of L. So we can write minus dz by dt, rate of decrease of z, is equal to rate of increase of L, that is dl by dt. So in place of dz by dt, I will take minus dl by dt. That's all. And dl by dt is nothing but speed of the stone, Vs. So 2 can be cancelled. X into speed of the box is equal to z into speed of the stone. We only want the magnitudes, ignore the minus sign. And x by z is nothing but cos theta. So speed of box cos theta is equal to speed of the stone. And that's what we got before also. Speed of stone is equal to speed of box into cos theta. So you can use trigonometry. Not trigonometry. Yeah, some trigonometry and Pythagoras theorem. That is one way to solve. There is a third method also to solve such problems. We make use of the idea that the string is inextensible. Okay, you cannot extend the string. Means the length of the string is fixed. Now, if the length of the string is fixed, the rate at which the length decreases on one side should be equal to the rate at which it increases on the other side. Okay, we'll make use of that. Rate of decrease on one side should be equal to rate of increase on the other side. Now see, the box is actually moving in this direction. If the box is moving this way, this end of the string, I'm calling one end of the string as A and the other end of the string as B. If box is moving to the right side, let's say with a speed VB, then the point A also is moving to the right side only. Let it move. So that's the velocity of one end of the string. Now that velocity VB, or okay, just to avoid confusion, I'll call it as VA, velocity of the point A. Okay. It's actually the box's speed. I'll call it as velocity of the point A. It's to the right side. Now that velocity of point A can be resolved into two components, one perpendicular to the string and one parallel to the string. Parallel to the string, it is VA cos theta. This VA cos theta is what shortens the string on this side. Do you all agree with this or not? The end of the string moves in some direction horizontally, but its component along the string is what makes the string shorter on that side. Correct or not?
Yes.
Pawan, do you agree with this?
Yes, sir.
Fine, it is like that. The velocity of end of the string along the length of the string is what makes the string longer or shorter. What about the other component? Can't it make the string longer or shorter? No, it can only make the string rotate. Fine, you can look at this pen moving if you want. Okay, I'm holding the pen at one end, so this end is at rest. The other end can move in a circle around this end, but if it is moving in a circle, it means its velocity is in the perpendicular direction. Okay, so the perpendicular direction only changes the orientation. It doesn't make, I mean, velocity in the perpendicular direction only changes its orientation. It doesn't make the pen shorter or longer. For the pen to become shorter, this end has to move this way along the length of the pen inwards. For the pen to become longer, it has to move the other way along the length of the pen outwards. So component parallel to the pen makes it shorter or longer. Component perpendicular to the pen only makes it rotate. It doesn't change its length. Same logic will apply to the what do you call string also. String's actual velocity is VA. We split it into two components, one along the length of the string and one perpendicular to the length of the string. The component along the length of the string is what makes it shorter on that side. And the other end, the string's velocity is in this direction itself. This is the velocity of B. Okay. VA cos theta is the rate of decrease of length on one side of the string. And VB as it is, VB is already along the length of the string, no, so no need to take its components. This complete VB is the rate of increase of length on the other side. And because the string is inextensible, these two must be equal. The rate at which length is decreasing on one side should be equal to the rate at which it is increasing on the other side. Therefore, okay, let's call them as V1 and V2. Therefore, V1 cos theta is equal to V2. That means velocity of the box cos theta is equal to velocity of the stone. And this is the relation that we got before also. So there are so many different methods to derive relation between velocities of 2 points of a string. Work done by tension can be used. Some geometry ideas can be used. X square plus y square is equal to z square. And this idea also can be used, that the rate of decrease on one side is equal to rate of increase on the other side. Okay. Fine. Let's move on. So last class we discussed about the condition in a rigid body. The distance between two particles of the rigid body should be constant. The body may rotate, it may move and rotate both at the same time. Okay. But the distance between two particles must not change. Now, it so happens that in rotating objects, different particles move with different velocities. So it's very complicated. You can't say, I mean, if you know the motion of one particle, you can't directly say how another particle is going to move. Okay. But to make things simpler, to help us analyze the motion of a rotating system much easily in a much simpler manner, there is one special point which helps. Okay. And that special point of the system is what we call as its center of mass. Center of mass of a system. Okay. We'll learn how to identify that point. Once you identify that point and you visualize how it is moving, you can describe the motion of any other particle of the rigid body very easily. Okay. So it's very, very important for you to be able to identify the center of mass of a system. Where is it? You have to find out. Okay. Now, if you know what it is, then you can tell where it is. So, definition of center of mass. Can any of you define? If you have already learned. Okay. It is the point of a system which behaves as if all mass of the system was concentrated at that point and all forces acting on the system were acting at that point. Okay. A point which behaves like this is what we call as center of mass. Okay. Now, any system you take in daily life or in real life, any object that you see around you, all its mass is not at one point. For example, this pen, its mass is distributed over a certain volume. Okay. Mobile phone, anything, a sheet of paper also, its mass is distributed. There's no single particle in real life actually. Okay. Maybe the only thing which you can call as a particle in real life is an electron. Okay. And who knows, electrons also could be made of something else. Okay. There's a lot yet to be discovered. Fine. So that particle idea is not applicable to real life situations at all. So anything that you see around you is a collection of particles. Mass is distributed. But for any collection of particles, you can identify one point which behaves as if all mass is concentrated at that point and all forces acting on the system were acting at that point. Now, how to identify such a point? Let's see. Consider a random system. Any object you can take. There'll be infinite number of particles in it. Okay, let's say there's one particle of mass small m1, another particle of mass small m2, another of mass small m3, and so on up to small m n. Let's say there are n number of particles. Then the total mass of the system becomes m1 plus m2 plus so on up to mn. We call it as, or we can denote it as sigma mi, where I varies from 1 to n. Okay, that's the total mass of the system. And depending on where it is, what it is surrounded by and all, there could be forces acting at different points of this system. When it's not necessary that force acts at only one point of the system. So M1 could be experiencing some force, call it F1. Okay, it's not just one of the forces. F1 is the net force acting on M1. Other particles of that system only may be exerting, or from some external agent may be exerting. But the resultant force on M1 is F1. Similarly, resultant force on M2, they need not even be the same. Okay, let's say F2. On M3, let's say the net force acting is F3. And so on up to the nth particle. On the nth particle, let's say there is a net force acting this way. Then the total force acting on this system will be the vector sum of these forces, F1 vector plus F2 vector, so on up to Fn vector. We can write it as sigma Fi vector, where I varies from 1 to n. Okay. So that's the total mass of the system and the total force acting on the system. Basically, the sum of forces acting on all elements of the system is nothing but its net force on the system. Okay. Now, by definition, center of mass is a point which behaves as if it has this much mass and as if this much force was acting on it. Okay, that's the definition of center of mass. You can't question that. Okay. Great scientists, they have done research and they identified that there is this magical point. If you can identify a point which behaves like this, it will help you solve problems. Solve not just problems, it will help you understand the motion of an object. Okay, and describe the motion of an object. So they identified that point should have these properties, that it should behave as if it has all this much mass, and it should behave as if this much force is acting on it. Okay. Now one of you tell me, if a mass m has a force F acting on it, then how much is its acceleration? If a mass m has a net force F acting on it, how much is its acceleration? You know net force and mass, how much is the acceleration? Pawan, your answer was not clear.
Sir, F by m.
F by m. Net force divided by mass is acceleration. Newton's second law. Okay. Now center of mass behaves as if it has this much mass and as if this much force is acting on it. Then by definition, the acceleration of center of mass of a system should be the net force acting on the system divided by the total mass of the system. Obviously, if it's a point which behaves as if it has all the mass and all the forces are acting on it, that point should have this much acceleration. Okay. Now net force on the system is nothing but force acting on the first particle plus force vector of the second particle plus so on, force acting on the nth particle as a vector, divided by total mass of the system is nothing but m1 plus m2, so on up to mn. Now tell me, can we write this as f1 by m1 plus f2 by m2, so on up to fn by mn? Can it be written like this? Quick, yes or no? Aishwarya, what do you say? Pawan, what do you say?
Total mass is equal at the right.
If masses are equal, we can write, you are saying. But generally,
No, sir.
okay. If masses are equal, are you sure we can write? Think about it. Saket, what do you say? Is it correct to change that equation to this, that expression to this? Okay. This is mathematically wrong. It will not, you cannot write it like this. Okay. Denominator cannot be split that way. Numerator, if you want, you can split. Anyway, I cannot teach you fractions now, but you can't split the denominator. You can write this as F1 divided by the entire mass plus F2 divided by the entire mass. That splitting can be done. Let it be. Now F1 is the net force acting on the first mass. Net force acting on the first mass will be first mass multiplied with acceleration of the first mass. Net force on the second mass will be second mass multiplied with acceleration of the second mass. And so on. Net force on the nth mass will be Mn An. Okay. So this gives us something else now. Therefore, the formula for acceleration of center of mass is m1a1 plus m2a2 so on up to mn an divided by the total mass of the system, m1 plus m2 plus so on up to mn. Numerator can be written as summation of mi ai vector, I varies from 1 to n, divided by the denominator can be written as summation of all the masses. So this is the formula for acceleration of center of mass of a system. Sigma mi ai divided by sigma mi. Okay. You can also just call it as net force divided by the total mass of the system. That is by definition of center of mass. Because center of mass is a point which behaves as if it has this much mass and this much force is acting on it. So directly net force divided by m. Now see, there is an important observation that you need to make here. If ACM, acceleration of center of mass, is F net divided by m, we can say that the net force acting on a system is the total mass of the system multiplied with the acceleration of its center of mass. Now we have been applying Newton's law, Newton's second law all this while, but we never talked about center of mass. We just used to write F net is equal to ma, F net is equal to ma, because all the objects we considered till now, none of them were rotating. Okay. Every particle of the object, whether it's a block or a ball, whatever it is, we assume they are all moving in the same manner, with the same velocity, with the same acceleration. But if an object rotates, different points can have different accelerations also. Infinite different particles of the system will have infinite different accelerations. Then if you want to apply F net equal to ma for that system, which point's acceleration is going to be used in that equation? Okay. Center of mass's acceleration is what you should use. When there's no rotation, you don't have to bother about anything. You can write acceleration of the entire object. But when there is rotation happening and you want to apply Newton's second law F net equal to ma, the law is applicable, the formula is applicable for acceleration of center of mass only. Okay. Other particles' accelerations will not be F by m, F net by m. They'll have different accelerations. Okay. So this is an obvious use of this point called center of mass. If you want to use Newton's second law, you need to know the center of mass. Fine. And this comes from definition of center of mass. Okay. We still have not discussed a way to find out where the center of mass is. We just know what acceleration it will have. Fine. I'll use this expression for acceleration. Can one of you tell me how to derive velocity from acceleration? Generally, if you know the acceleration of an object or a particle, how do you derive its velocity? Yeah, from acceleration, how to find out velocity after a certain time?
V2 minus V1 is equals to
V2 minus V1 equal to?
అంటే V minus is equals to A.
Tell properly. V minus u is equal to?
Sir, V minus U equals to A.
V minus u is not A. How can final velocity minus initial velocity become acceleration? You removed one term.
Sir, acceleration and time will be equal to change in velocity.
Okay. V minus u is equal to, that is change in velocity is equal to acceleration into time. Fine. That is if acceleration is constant. You are using equations of kinematics. But generally, change in velocity, delta V, will be integral A dt. You integrate acceleration with respect to time, you can get change in velocity. From that, you can try to find out velocity. Okay. Now we know the formula for acceleration of center of mass. From the definition, it's this. You integrate both sides with respect to time now. So integral ACM dt, which is equal to integral this whole thing dt. You can write it like this. And integrating acceleration, you get change in velocity. So the left-hand side can be written as VCM plus some constant. Okay. Generally, when you integrate indefinitely without limits, you have to add a constant, unknown constant. Should be equal to right-hand side. Capital M is the total mass of the system. It is constant, bring it out. 1 by M, total mass. You are integrating n terms inside. Integral M1 A1 dt. Okay, let me write that. First integral will be integral M1 A1 dt. M1 constant, no, I'll put that also outside. Mass of the first particle. M1 integral A1 dt plus M2 integral A2 dt. See, these derivations are important. I suggest you do them once on your own later. M3 integral, sorry, Mn integral An dt. That is the integration on the right hand side. And again, integral of acceleration with respect to time is nothing but velocity of that particle plus some constant. I'll call it C1. Similarly, integral of acceleration of the second particle with respect to time is velocity of second particle plus some constant. Similarly, nth particle, velocity of the nth particle plus some constant. Remove all the constants. See, constants can be there. The constants can be zeros also. Okay. So for that point called center of mass, we assume the constants to be zeros. Therefore, we get velocity of center of mass as, what is there on the right hand side? M1 V1 plus M2 V2 plus so on Mn Vn divided by total mass of the system. This is the basic formula for velocity of center of mass. You can write it this way. Vcm is equal to sigma, that is summation of mi vi, where I varies from 1 to n, divided by summation of mass of the ith particle. Again, I varies from 1 to n. This is the basic formula for velocity of center of mass. And it's very similar to the formula for acceleration of center of mass. Okay, acceleration was sigma mi ai divided by total mass. Velocity of center of mass is sigma mi vi divided by total mass. Okay, and there's another way also of looking at it. One of you tell me, what is mv, mass into velocity?
Momentum.
Momentum. So mi vi is nothing but momentum of the first particle, m1 v1. m2 v2 is momentum of the second particle. So on up to mn vn is momentum of the nth particle, and you are adding all of them up. So this becomes the net momentum of the system divided by total mass of the system. This is another use of center of mass. Yesterday, we had some problem, okay, when systems rotate. When systems rotate, different particles have different velocities. So momentum of the first particle is this, momentum of second particle, so on up to momentum of the nth particle. You can't take anything common in these terms. Infinite different particles, infinite different velocities. So we were wondering how to calculate the momentum of such a system. Center of mass has given us a solution to that. We still don't know what is the center of mass, where is the center of mass, but if you can identify that point, you can tell the momentum very easily. So from this equation, we can say that the net momentum of a system is the total mass of the system multiplied with the velocity of its center of mass. Infinite particles will have infinite different velocities. Let them die, whatever. If you know how the center of mass is moving, you can tell the momentum of the entire system at once. Okay, this is another very important use of the point called center of mass. Fine. This also comes from definition of center of mass only. That acceleration equation we integrate, we get the velocity of center of mass. And from velocity of center of mass, we get momentum is equal to mass into velocity. So for a rotating system, or for a system in which different particles move with different velocities, if you want to write an expression for its net momentum, just take the velocity of its center of mass. That's all. Next, if you integrate velocity, what do you get? Anyone? If we integrate velocity with respect to time, what do we get? Someone unmuted, but I didn't hear what you said.
Displacement.
We get displacement. Displacement is nothing but change in position. You can write final position minus initial position, or you can write final position plus some constant. Okay. We'll do the same with center of mass also. We know velocity of center of mass is m1 v1 plus m2 v2 so on up to mn vn divided by total mass of the system. Integrate both sides with respect to time. Nothing wrong in doing that. And left hand side, you are integrating velocity of center of mass. The left hand side then becomes position of center of mass plus some constant. We'll again make that constant 0 only. And right hand side, mass is constant. Total mass of the system is constant. Put it outside. You will be left with integrals like this. m1 integral v1 dt plus m2 integral v2 dt so on mn integral vn dt. And integral v dt is displacement of that first particle. No? So position of the first particle plus some constant. Similarly, v2 dt is position of the second particle plus some constant. Position of the nth particle plus constant. Assume all constants to be zeros. This will lead us to the position of center of mass. Okay, center of mass is that point for which these constants are zeros. Right? You can identify other points also with some non-zero constants, but never mind. You don't have to bother about them. So what will you be left with on the right hand side? m1 r1 vector plus m2 r2 vector. R1 is the position of the first particle, R2 is the position of the second particle, so on. Mn Rn divided by total mass of the system. This way you can identify where the center of mass is. Therefore, the general formula for position of center of mass becomes summation sigma mi ri vector divided by total mass is nothing but summation of individual masses, sigma mi. So acceleration of center of mass, velocity of center of mass, position of center of mass, the formulas are all similar. Fine. And there's nothing particular that you can get from this. This equation helps you identify where the center of mass is. So you can use this to locate the center of mass. Okay. Let's make use of the ideas that we discussed till now. First, suppose there is a system with 3 particles. One particle here, one particle maybe here, another one here. So let's say this particle mass is 2 kg. A particle having 2 kg mass is hypothetical actually. Let's say this particle mass is also 2 kg. This is 1 kg. One of them is at the origin, you can clearly see. The other one, okay, let's name them as A, B, and C. See, A is at the origin. Position of B, let's say, is 10, 0. It's on the x-axis, no? So 10, 0. Position of C is 0, 10. It's on the y-axis. Identify the position of center of mass of this system. Okay, write the positions as vectors. So this is 10 I cap. This is 10 J cap. The third one's position is 0. Derive the position of center of mass of this system. Make it fast. I got one answer as 4 I cap plus 2 J cap. We'll see. So you just have to directly substitute in the formula. Pawan, can you tell me the formula for position of center of mass?
MRCM, MR by RCM. Summation of them.
Tell properly. Summation of
MIRI by
MIRI divided by
total mass.
Total mass. Summation of all the masses. Okay. So here there are 3 masses. Therefore, the position of center of mass of this system will be, first mass is 2 kg, that is A. Its position vector is 0. Second mass is 2 kg, that is B. Its position vector is 10 I cap. Third mass is 1 kg, that is C. Its position vector is 10 J cap. Divided by total mass of the system, 2 plus 2 plus 1 is 5. That's all. So this becomes 20 I cap plus 10 J cap divided by 5. That is 4 I cap plus 2 J cap. Basically, that means 4, 2. 4, 2. Okay, 4 here, 2 here. The center of mass of this system lies here. Okay, I'll call it as O. That point is the center of mass of this 3-particle system. Any doubt in this solution? Okay. Now see, position vectors usually have X components, Y components. In 3D, they can have Z components also. Now we know that position of center of mass is sigma mi Ri divided by sigma mi. Now when you add these vectors now in the numerator, you are going to add X components, Y components, Z components separately. You will never combine X and Y components. Okay. So you can also write like this. X coordinate of center of mass. If you only want the X coordinate, you can take it like this. Sigma mi xi divided by total mass of the system. If you only want the Y coordinate of center of mass, sigma mi yi divided by total mass of the system. And if you only want Z coordinate of the center of mass, sigma mi zi divided by total mass of the system. You can get separate components like this or separate coordinates like this instead of writing I cap, J cap every time. Okay, we'll stop it here for today. So we discussed how to get the constraint relation in this case, like how to find out the relation between the velocities of the two ends of the string. I told you 3 different methods. Then we talked about this point called center of mass of a system, which makes it easy for us to analyze the system. And you already saw how it makes things easier. If you want to apply Newton's laws, you have to apply to the center of mass only. Okay, by definition. If you want to find out momentum of a system, you have to find momentum of the center of mass. You don't have to find momentum of each particle separately. Okay, and for that you need to identify where the center of mass is, and this formula helps us locate the center of mass. And we did that in one case. Fine. Next class, maybe 1 or 2 classes following this, we will be locating the center of mass of different systems. Okay, we'll be applying this formula. Now see here in this problem, there were 3 separate particles, so it easily we could solve. But in any real life object, there are infinite particles. For such continuous mass distributions, How to locate the position of center of mass is what we'll discuss over the next few classes. Okay, very, very important. This is one of the core ideas in your entire physics syllabus. Okay, don't miss any class from this chapter. Okay, thank you all. We'll continue in the next class.